Ever stop and think about what makes your phone, your computer, and even the entire internet feel so ridiculously fast? Well, there's this unseen superpower humming along in the background. It's a total shift in thinking that powers pretty much every piece of tech we use. Today, we're going to pull back the curtain on that exact idea: parallel computing.
All right, let's just dive right in with a huge question that kind of stumped engineers for decades. If we want something to be faster, why can't we just build one computer chip that gets faster and faster and faster forever? Turns out, there's a limit, a very real, physical wall that we slammed right into. You see, for years, the whole game was just about raw clock speed. Think of it like trying to make a single runner sprint faster and faster. But we eventually hit a point where we couldn't push any harder. The chips were getting so hot they were literally in danger of melting themselves. It became super clear that we needed a completely new strategy.
And this just nails the difference between the old way and the new way. On the left, you've got serial computing. It's like one person trying to do all the work, one task at a time. I mean, it gets the job done, but it's slow. On the right, that's the light bulb moment. That's parallel computing. You just get a team to help.
Yeah, this whole teamwork idea was the big breakthrough. It completely shattered that old speed limit. Instead of trying to make one single worker impossibly fast, the brilliant new question was, hey, what if we just hired more workers? And this simple idea has a name, and it's the heart of everything we're talking about.
So here's the official definition. The key here is that we're still solving one single problem. We're just using a lot of hands, or, a lot of processors, to get it done at the exact same time. It's all about collaboration, just on a microscopic scale.
So, what's the game plan? Well, it's actually a pretty simple four-step process. First, you take a huge problem and you divide it, breaking it into smaller, bite-sized chunks. Then, you assign each of those little chunks to a different processor. Step 3 is the magic part. They all execute at the same time. And finally, you just combine all their individual results to get the one big final answer. Simple, super logical, and incredibly powerful.
Okay, let's make this feel a little more real. Imagine you've got a massive task, like you need to process 1,000 different images. Maybe you're adding a filter or resizing them. Now, doing that one by one would take forever.
And just look at this difference. With the old serial computing method, that one lonely processor has to chug through all 1,000 images. Let's say that takes 100 minutes. But with parallel computing, we can give 10 processors just 100 images each. And since they're all working at the same time, the whole job gets done in just 10 minutes. That is a 10 times speed up.
Now, this isn't just some neat theoretical trick for processing photos. This concept, this idea of teamwork, is the engine that runs our entire modern world, from huge scientific breakthroughs to the apps you tap on every single day.
In science and engineering, it's not just useful, it's absolutely essential. Think about trying to forecast a hurricane. You have to process this unbelievable amount of data, wind speed, temperature, air pressure, all at once. That's a perfect job for a parallel supercomputer. And that same thinking is used for everything from designing rockets to mapping the human genome.
And it's not just for massive science projects. In medicine, right? When you get an MRI, that machine is capturing millions of data points. A parallel computer is what takes all that raw data and builds a 3D image of your body in just minutes. Businesses use this same power to analyze huge data sets, and scientists use it to discover new life-saving drugs.
And of course, it's behind all the fun stuff. All the stunning 3D animation you see in movies, the incredibly immersive worlds in video games, even the simple act of streaming this content right now. It's all being handled by massive parallel systems out there in the cloud.
Okay, so we know it's fast, we know it's everywhere. But how does it actually work, down inside the chip? Let's take a quick peek under the hood and look at a couple of the really clever tricks that make all this possible.
So the first trick is this thing called pipelining. And honestly, the best way to think about it is a factory assembly line, right? Instead of building one entire car from start to finish before even starting the next one, you have different stations and each station is working on a different car at the same time. So how does that assembly line look inside a CPU? Well, basically, every command your computer gets is broken down into a few simple steps. First, it has to fetch the instruction, kind of like grabbing the blueprint. Then it decodes it to figure out what to do. Next, it executes the actual work. Sometimes it needs to access memory for more data. And finally, it writes back the answer. The real key, though, is what happens when you have a whole bunch of instructions lined up.
And this right here is where the magic happens. Just look at what's going on by the 5th tick of the clock. Every single station on that assembly line is busy. One instruction is being fetched, while another is being decoded, a third is executing, all at the same time. The line is full, and the computer is just humming along at maximum efficiency. This is what's known as throughput, and it's a huge reason your computer feels so snappy.
So pipelining is fantastic for making one processor faster. But what if you have thousands of tiny processors all working together, like inside a graphics card? Well, that's where another brilliant idea comes into play. And it's basically the secret sauce behind modern gaming. It's called SIMT.
And to understand it, just picture a classroom. The teacher stands up at the front and gives one single instruction to the entire class. Everyone, add 5 to your number.
Now, every student does the exact same thing. They add 5, but they each do it to their own unique number. And that's it. That is precisely what SIMT means. Single instruction, multiple threads. A graphics card is like a giant classroom with thousands or even millions of these tiny processors called threads. It gives out one instruction, like make this specific pixel brighter, and millions of threads all execute that command on their own pixel, all at the exact same instant.
So when you boil it all down, the great leap forward was moving from a single worker to a massive coordinated team, from serial to parallel. And that one shift has unlocked possibilities we could only dream of just a few decades ago. Which really leaves us with one last big question. Now that we've taught our machines how to work together, what's the next great challenge that we can all solve?